So this video is on electrolysis. It's a paper 1 only topic that you would have done in year 10. If we start by looking at the word electrolysis, it literally means electricity to split something up. So electro is electricity and lysis means split. And you're going to use electricity specifically to split up an ionic compound. Now, when we're looking at electricity, there are two types of current. There's AC and DC, and in electrolysis, we use DC, direct current. And we use it to split up what's called an electrolyte. Okay, now what is an electrolyte? An electrolyte is an ionic compound. Now remember, if it's an ionic compound, you've got a metal and you've got a non-metal, but because we're using electricity, the ionic compound has to be able to conduct electricity. And ionic compounds only conduct when they're liquid or when they're aqueous. So an electrolyte is an ionic compound that conducts electricity, and in order for it to conduct electricity, it has to be liquid or it has to be aqueous. And you do need to be able to explain why, okay? When it's liquid or aqueous, it has ions that can move. When it is present in solid form, the ions can't move, so we say we've got no mobile charged particles. If I had a solid ionic compound and I wanted it to conduct electricity, all I would need to do would be melt it or dissolve it. Right, I want you to press pause and have a go at doing the first 4 questions. Alright, so what is electrolysis? Okay, it's using electricity to split up an electrolyte. An electrolyte is an ionic compound, so I put that in brackets. What type of current do we use? It's always DC, direct current. Okay, what exactly is an electrolyte? So I've already told you that an electrolyte is an ionic compound, but more specifically, it's an ionic compound that can conduct electricity. And to conduct electricity, the ionic compound must either be aqueous or molten. And that means it's going to have free moving ions. The ions will move freely, allowing it to conduct electricity. Why is solid not an electrolyte, and how could you make it an electrolyte? Now, if it's solid, the ionic compound cannot conduct electricity. The reason why, it doesn't have any mobile charged particles. So anytime something doesn't conduct electricity, you just say it has no mobile charged particles. Now, in order to make it conduct electricity, because it's an ionic compound, I just need to make it aqueous or molten. To make something aqueous, I dissolve it in water. To make something molten, I would melt it. Alright, so here I've got 2 examples of electrolytes. I've got sodium chloride, which is ionic and it's liquid, so it conducts electricity. And I've got iron bromide. Again, it's ionic and it's liquid, so it conducts electricity. And we said we're going to use electricity to split it up. When I split it up, I get the elements. So sodium chloride contains sodium and chlorine. So when you split sodium chloride up, that's what you get. Iron bromide contains iron and bromine, so when you split it up, these are the elements that you get. So how exactly does it work? Okay, well, we said we're going to use electricity, and if I'm using electricity, I'm going to be using a battery or a power pack. So I've represented that just by a plus on one side and a negative on the other. I'm going to use electricity to split up my electrolyte. Now, my electrolyte is going to be in liquid form, and I put my electrolyte into a beaker. But I need electricity to be able to get from the battery into the electrolyte. And to do that, I'm going to attach what we call electrodes to the battery. So I'm going to attach one electrode to the positive side of the battery and the other electrode to the negative side of the battery. Alright, so that's an electrode. And then in this beaker, I'm going to have my electrolyte, and you have to draw the level of the electrolyte above the electrodes. Alright, the electrodes have to be submerged in the electrolyte. So here is my electrolyte. And then what will happen is you turn your battery on, electricity will flow through these electrodes into the electrolyte, and the electricity will split up the electrolyte. So if sodium chloride, liquid, if that was my electrolyte, then it would split it up into sodium and chlorine. I'll talk a little bit more about how it does that in a second, but that's what it's going to do. Now, when we're looking at electrodes, you need to know what you can use as electrodes. And you can use a number of different materials as electrodes, as long as they fit the following 3 criteria. Okay, so the electrode has to be inert, and that just means unreactive. You don't want the electrode and the electrolyte to have a chemical reaction, so we use something really unreactive as our electrode. The other thing it absolutely has to be able to do is conduct electricity. You need the electricity to flow from the battery through the electrode and into the electrolyte. So these guys have to conduct electricity, all right, that's really important. And the other thing you can say is that they'll need to have a high melting point, because often we carry out electrolysis at high temperatures and you don't want the electrode just to melt. So we want them to have a high melting point. Now there are two things that are typically used. One is graphite. So graphite fits all three criteria. It's unreactive, so it won't react with the sodium chloride electrolyte. It can conduct electricity because it has delocalized electrons. And because it's giant covalent, it has a really high melting point because we've got lots of strong covalent bonds. I now want you to have a go at doing questions 5 and 6, okay? In 5, when I say draw the apparatus, you have to draw that diagram, okay? And just make sure that when you're drawing your electrolyte, that your electrodes are in the electrolyte, okay? So have a go doing 5 and 6. All right, so this is what you should have drawn for 5. You're drawing me a battery, okay, positive and negative, and you're drawing the electrodes attached to that battery, and then the electrodes have to go into the electrolyte. So for example, if you did something that looked like this, if you had your electrodes, and then you had your liquid starting down there, that would be wrong, okay? They have to actually go into the liquid. Why is graphite a suitable material? Well, graphite can conduct electricity, but tell me why. They love to ask that. It's got delocalized electrons, so it can conduct. The other thing is it's unreactive, that's what inert means, and it won't react with the electrolyte. Alright, so we're going to look at this process in slightly more detail. So I've drawn the same diagram again, but next to the positive end of the battery, I've called it the anode. And next to the negative end, I've written cathode. And you do need to remember this, but we've got a little memory aid. Panic, okay? So P-A-N-I-C, positive is the anode, and negative is the cathode. And that will help you remember that positive is anode, negative is cathode, okay? And what they're going to ask you is they're going to ask you what forms at the cathode and what forms at the anode, okay? So we're splitting up ionic compounds, okay? Ionic compounds are made of metals and non-metals, and metals are always positively charged ions and non-metals are negatively charged ions. Now you need to know that opposite charges attract, and that means whatever is positively charged is going to go to the cathode. Now the metal is always positively charged, so the metal is always going to go to the cathode. The non-metal is negatively charged, it will be attracted to the positive anode, so at the anode I always get the non-metal. So for example, alright, if I was giving you sodium chloride, NaCl, if that was my electrolyte, sodium is the metal. So the first word is always the metal. So sodium is the metal is positive, the metal goes to the cathode. So at the cathode, you are going to see sodium form. The non-metal is chlorine, the non-metal is negative, negative goes to the anode, so at the anode I'm going to see chlorine form. And in terms of what you'll actually see, because sodium is a metal, and it's solid, you'll see solid metal build up around the cathode, and the cathode is going to get bigger because of all that solid metal building up. Chlorine is a gas, and because it's a gas, you are going to see bubbles at the anode, and that's how you'll know chlorine gas is being produced. Now, something else I just need to go through, all right? When it's molten, so when you've taken an ionic compound and you've melted it, then at the cathode you always get the metal, and at the anode you always get the non-metal. So that's straightforward, okay? But if your ionic compound is aqueous, so you've dissolved it in water to make it conduct electricity, then the aqueous, all right, means you've got water present. And if you've got water present, water can split up into H plus and OH minus. So we saw these ions last time when we were looking at acids, but water can split up into H plus and OH minus. And because the hydrogen is positive, hydrogen will also go to the negative cathode. Now the OH minus ion isn't going to cause us any problem, but the H plus is going to go to the cathode as well as my positive metal. All right, but you can learn a rule, okay? At the cathode, if it's aqueous, hydrogen will always be the product unless the metal in your ionic compound is copper. Okay, so I'm going to give you two examples. Sodium chloride aqueous, copper chloride aqueous. Okay, when it's aqueous, at the cathode you will always get hydrogen. Okay, so I'm going to be forming hydrogen unless the metal is copper, in which case you form copper. Now if it's not aqueous, if it's molten, so if I had NaCl that was liquid, then there's no hydrogen present, and it's just this rule. Cathode is the metal, so that would be sodium. So liquid, metal at the cathode, but aqueous, hydrogen at the cathode, unless that metal is copper. Non-metals are a little bit easier, okay? When it's molten, the non-metal goes to the anode, and when it's aqueous, the non-metal goes to the anode. Your only exception that you need to remember is sometimes the non-metal will be sulfate. Okay, so sulfate is SO4, so you've got sulfur and oxygen in sulfate, and if you've got that, then oxygen is going to be a product every single time. All right, I know that's a lot, but let's try and do some practice questions. All right, so in 7, have a go at completing that table. Okay, even if you get it totally wrong, just have a go. Do 7, 8 and 9 and then press pause again, or sorry, press play again. Oh sorry, I should have said don't fill out the ions bit. I've scribbled that out. Don't do the ions bit, just do product at cathode and product at anode. Alright, so hopefully you've given this a go. So my first electrolyte is sodium chloride, and it's molten, and that just means that the metal goes to the cathode and the non-metal goes to the anode. The next one, potassium bromide, lithium chloride, they're all molten, so that just means metal to the cathode, so sodium, potassium, lithium, non-metal to the anode, chlorine, bromine, chlorine. But the next 3 examples are aqueous, and if it's aqueous, the rule is always hydrogen at the cathode unless the metal is copper. Now there's no copper here, which means I've got hydrogen at the cathode every time, and then the non-metal goes to the anode, so these answers are the same as before, chlorine, bromine and chlorine. So the non-metal bit is okay, the anode's okay, it's just the cathode you really need to pay attention. Is it molten or is it aqueous? Now I told you your exception was if the metal was copper, copper is going to form. So in question 8, what always forms at the cathode? It's copper. If copper's there, copper is your product. Number 9 then, if you have sulfate, so I haven't given you any of those examples there, but if they gave you sulfate, you are going to form oxygen. So just pay attention. If it's sulfate, it's sulfur and oxygen is what forms. The very last question here. Products when acidified water is electrolyzed. So water contains hydrogen and oxygen. Hydrogen, from your acids topic, has a plus charge, so hydrogen goes to the negative cathode. Oxygen is in the OH minus part, and the negative OH minus goes to the positive anode, and you get oxygen. So if you want to split up water, you're going to get hydrogen and oxygen at the cathode, oxygen at the anode. Okay, we'll obviously do lots of exam question practice on this in class as well.